All right, welcome everybody to our PyMC webinar. I'm very excited to have you all here and to present our amazing speaker, Ricardo, who will be talking about PyMC, Aesara, and AePPL, the new kids on the block. I wanted to call it the cool kids on the block, but that was dismissed. Before I'll introduce Ricardo and we get into the actual talk, I just wanted to basically give a bit of background and some announcements. Ricardo and I, we both work at PyMC Labs, and this is our amazing, cool new Bayesian consultancy, which basically is a whole bunch of the PyMC core developers teaming up to solve whatever hardcore business problems we can come across and apply Bayesian modeling in PyMC to. And I really couldn't be more happy about the team that we have. I mean, it's all of us who have been working together for many years already on PyMC, and now basically redirecting that to solve your business problems. And yeah, so very happy with the people we have from all kinds of different backgrounds. Most of us actually coming originally from academia, and yeah, that's where we fell in love with Bayesian modeling, and now can turn that into our day job. We mostly, well, we do a whole bunch of stuff, all centered around PyMC and Bayesian modeling. Just a couple to highlight. I mean, one thing actually that fairly often is something that we get requests for is speeding up models. Like someone already has built a PyMC model and they're really happy with it, but it takes 6 hours to run, and then we, I don't know, get that down to 30 minutes, 10 minutes. And then from there, often that allows more breathing room to actually then extend the model further and add more structure to it, make it hierarchical, and all in the purpose of maximizing the value of that the model has, right? Like improving the accuracy. But yeah, and the other thing, of course, that we do is training and workshops. So these have been very popular. This is just yeah, if you are interested in that, just email me, Thomas Wiecki at pymclabs.io. You can also follow me on Twitter. Here, just some links. So our website, and there's a whole bunch of blog posts, pymclabs.io, and that's where we also find more information about the workshops. Here are a whole bunch of links for general PyMC. So if you have questions on the software, then you can find us on Discourse. Of course, the code and everything lives on the GitHub. Our main page actually isn't listed here, but it's pymc.io. So that's really the main entry point, and then it will have links to everything else. Announcements you can find on our Twitter. For PyMC, it's PyMC Devs. We also have a Labs account, PyMC Labs. We're on LinkedIn, if you hang out there. And then our YouTube channel, where this talk will be posted, and a whole bunch of other materials and talks can be found. And we have a code of conduct, which we ask everyone to follow, which you can read up on here. Also, we have a Bayesian course that we developed. This is with Ravin Kumar and Alex Andorra. And this is basically a self-paced learning course. We really focus on teaching the intuitions behind it and using that illustratively through code and using PyMC Labs, rather than just like give you the math. Like, this is really the result of my own frustrations with how I had to learn Bayesian modeling with like textbooks and like conjugate priors and all kinds of obscure stuff that actually no one really cares about today. So this is like the updated version that really like cuts to the chase and hopefully gets you allowed to start quickly. And with a focus for data scientists and Python developers, so people who already know Python, but maybe have frequentist background. So this is who it's geared towards. And it's using videos and code. So that's intuitivebase.com. Well, this is really what we'll be talking about a lot today, PyMC 4.0. Actually, now already 4.1 is here. We couldn't be more excited about this release. It's been taking us a really long time to get there. It's more or less like a major rewrite of PyMC and of the core underlying features. And this is really what Ricardo's talk is going to be about. Some of the really exciting features are the new JAX backend. So there also with PyMC Labs, we've been able to now like build models of like unparalleled scale, where with hundreds of thousands of data points, hundreds of thousands of parameters, like very complex hierarchical Gaussian process models. But on the GPU with JAX sampling, they fit in an hour. So the scale is just something completely new. So GPU support is something that is like really exciting. But also, as you might have know, Theano has been discontinued, so we had to find a new backend. So we decided to fork it, and this is work that Brandon Willard is leading. Is now called Aesara, which you'll be hearing much more about, and a whole bunch of like things that have always been annoying for mainly the developers were now fixed, where we'll really have like such a much more powerful base to build on and really enhance many things. And there's like better nuts initialization, and also actually our installation process is much more simplified thanks to Ben Maris, who has just joined. So you can really just do conda install the C conda forge PyMC, and no matter which platform, it should just give you the compilers and everything, and you shouldn't need to worry about anything. So yeah, that is cool. And so now let me introduce Ricardo, who's a good friend of mine, co-developer of PyMC and a colleague at PyMC Labs. So he really has been like the main developer of PyMC in at least the last year, and PyMC 4.0 is largely to his hard work on this in like all the different domains, and also then our Aesara and AePPL. So there really couldn't be a better person to talk about really the technical underpinnings. So yeah, it's really cool to have him here. He is self-taught, which is really impressive for what he's able to do in statistics and computer science at the expense of his official degrees in psychology and neuroscience. So like many of us, he's a recovering academic. Follow him on GitHub. It's actually hard to keep up with him there. So you can also follow him at Twitter for announcements. He has a cool blog and of course the PyMC Labs website. So with that, I give it over to Ricardo to tell you about all the cool new developments and really the things underneath the hood and what makes PyMC 4.0 as powerful as it is. So with that, thank you. And it's actually big enough, but if you just zoom in once or twice, probably it'll be even easier to read.
Yeah, we'll see about the outputs, but yeah.
Yeah, okay, that's perfect.
Okay. All right, thanks for the very nice intro. If you folks want to check the notebook, I think it's just slightly updated from the presentation. You can just write this link. I'll share it in the chat. Okay, so today I will give an overview of how PyMC 4.0 is built, and mainly how it makes use of two very cool libraries, Aesara and AePPL, or AePPL, we are still debating the name, to give the cool functionality that PyMC offers for the whole Bayesian workflow. I will assume you already used PyMC or you are familiar with the PyMC API, so I will not dwell on that. I will just use it. And actually, during this talk, I will perhaps show you how you would implement 90% of PyMC features by just understanding what Aesara and AePPL can offer you. All right, this will be, I will run this notebook live, so let's hope it's fast enough. Here are the new or the cool kids on the block. We'll import AePPL, Aesara, and PyMC. with the common aliases, and I'll be using this version, so PyMC 411, Aesara 274, and AePPL 0031. And I'll also do import Aesara.tensor SAT, which is quite commonly used, and I will just explain what we can do with these things. So Aesara, we already had a bit of an introduction. It's our fork of the Tiano library, which was a quite popular Python library for tensor operations, mostly used for deep learning back in the days, but which was actually much more flexible and hackable. And PyMC 3 was built on top of Tiano, and now PyMC 4 is built on our fork of Tiano Aesara, which still shares most of the cool features that Tiano had, and also some new things. So just a quick overview, Aesara, what it does is offers you a way to create graphs that do tensor operations that follow the Numpy API. So things like broadcasting, indexing, just like you are used with Numpy, and most of the functions you find in Numpy, you'll find in Aesara. It goes beyond Numpy in that it tries to, it can be used to compile these graphs into very efficient code that you can call from PyMC. We can compile to C code and now to Numba and JAX as well. And obviously it supports auto differentiation. And also it has some routines to optimize graphs and to manipulate graphs, which come very in handy in a probabilistic programming language like PyMC. And we'll talk a bit about today. It also has very good support for graphs based on random variables to be able to take random draws from some distributions and then operate on them just like any other tensor variables. So very quick crash course on Aesara. I will go line by line. Feel free to, after I finish this section, just write questions you have in between, and maybe I will answer one or two that are more relevant. So we'll just start by creating two input variables. Will be x, which will be a scalar variable. It will be a float scalar variable, and y will be a vector variable. We'll combine them by just adding x plus y, saving this in z. And once we actually use this and evaluate a graph, it will broadcast just like NumPy. So our scalar x will just broadcast into the shape of y, which is a vector. I'm just giving names just to show then in the debug, this is optional. And then once we have z, I will just take the log. Usually you can do at.some function, which is, you have almost all the equivalent ones that you would have for NumPy. So if you do numpy.log, you'll have a at.log. And so we save the log of z in w. And we'll just have a look at what this graph looks like by using a Aesara dprint, which stands for debug print. This is very helpful to understand Aesara graphs. It's a bit verbose and a bit confusing at first, but you'll get used to it. So we just start reading from the output w to the inputs, which are nested inside. So w is a log operation that's applied element-wise to all the values of w. The input of this log is an addition operation that's also element-wise, which has two inputs, y, our vector, and x, a dim shuffle of x, which just means broadcasting x to the shape of y. Then once you have a graph and you actually want to do computations with it, you call Aesara.function. You specify the inputs, in our case x, y, and the output w. And once in this process is where the graph is compiled. By default, it will compile it to the C backend. After you compile into a function, you can then evaluate it. In this case, we'll just call with x equals 0 and y 1 and e, which you just take the log of y. And we get the output 0, 1. If you are in a hurry or you are just trying to debug or prototype, you can call on any variable called that variable.eval, and then pass the inputs in a dictionary. And behind the scenes, it will just compile the function and call it with these values. And this is just handy if you just want to debug and see if it's giving you the numbers you would expect. And finally, I presented you the graph going from x, y to W, but actually with Aesara you can define any intermediate graph with any number of inputs or outputs. So we can also just say, okay, we'll use Z as the input and W as the outputs instead of X and Y as the inputs. And now this is just a function which it basically takes a vector because Z is a vector and takes the logarithm of that vector. And indeed, we can compile, evaluate, and we get the logarithm of what we passed as input. The second cool thing is we can specify different computational backends for our functions by just passing a different mode. In this case, we'll just compile this function to Numba, and this is running Numba code when we call Numba or Numba. I never know how that should be pronounced, and equivalent to JAX. We can call it, we'll get a warning that you can ignore for now, but indeed, this is all being computed in a JAX JITted version and giving you back the output, a device array. Next big offering of Aesara is automatic differentiation. We'll just do a simple graph which has a scalar x and take a logarithm of that. And if you want a gradient, you can just call at.grad, specify a scalar cost, and with respect to which variables you want the gradients. So in this case, we'll just get the gradient of y with respect to x. Then we compile this function. You can actually have a function with multiple outputs. So we'll say we want y and the gradient of y with respect to x as the outputs and the input x. So we get both the value and the gradient. You can also deprint a function once it's compiled, which will follow the same kind of deprint you saw for graphs. And we see we have two outputs, just the log of x and the gradient, which is a reciprocal of x, if you remember it from calculus classes. And indeed, when we evaluate, we got what we would expect. When you compile an Aesara function, actually Aesara looks to see if your graph can be optimized or if it can be converted into an equivalent graph that's more numerically stable. And this is really nice because you can just write the graph that you know is numerically correct without having to worry about will this be like stable under float operations, or is there another operator that would be faster to do this, because Aesara will just replace these things when you compile. Here I'll show you an example. We're just taking a matrix x as an input, and we'll take the logarithm of 1 minus the exponent of x. This is an expression that appears quite often when working with log probabilities or log cumulative functions. And this is how the graph looks like when we just define it. Then we can compile it, and we can actually deprint, and we'll see the compiled graph looks quite different than the original one. Because it introduced this specialized operator, which is log 1 minus x, which is just more numerically stable than the naive way of computing y like this. Another way that it's that Aesara produces efficient code is it avoids recomputing the same operations twice. So if you have a function of two inputs and it's the same function and the same inputs, it will just compute it once. This only happens after compilation. So here the graph has the two exponent of x and then adds them. But once we compile it, it will be clever and we'll just compute the exponent of x once and then add it twice. And yeah, next step is Aesara. The reason we always talk about graphs and then functions that can be evaluated is that Aesara has very strong graph manipulation features, which are really cool when you want to do graph manipulation, which you often want to do in a Bayesian setting, especially if you are developing a library for users. So I'll just give a quick example. Again, something simple. Let's just have two scalar input variables, x and lambda. And I'll just create a variable that I call PDF of x, which I think is just the PDF of an exponential distribution evaluated at lambda and x. I'll use the helpful eval to just debug it. I get the number. And then if I wanted to say that instead of providing x, I want to provide the logarithm of x, this is, for instance, used if you are doing optimization and you want to be able to offer any value as input, not just valid values that must be positive in the case of the exponential distribution. You can do that. And so here what we do is we call Aesara clone replace. We say, I want as the output my PDF X graph. this expression, but now I want you, wherever there was x, I want you to actually use the exponent of x. Okay, so now when I evaluate this expression, I pass 0 instead of 1, but I'll get the same output because it will be just exponentiated before it's evaluated downstream. And last but not least, Aesara developed random variable operators, which are all about creating graphs with that take random draws, and they have a very nice, well structured API that makes our life very easy in PyMC, as we'll see later. This is going to look a bit messy, but just bear with me. I will just show you the minimal way of creating a random variable graph in Aesara. We'll start by creating a scalar location variable and a scale, which will be a constant variable. Instead of something we input, it will always be 1.0. I would be able to just use a Python float or an integer or a Numpy array, but under the hood, and it's good to know, it's always converted to a constant in these cases. So we just go ahead and create it directly. And then I will create another constant, which will be a random number generator state, which we just create with NumPy, random default RNG, we pass a seed. But instead of being let's say a classical constant, it will be a mutable constant, which in Aesara are called shared variables. So you can think of this will be a constant, but we can change the value across calls. And you'll see why this is useful in just a bit. But so once we have these three variables, we can go ahead and create a random normal variable, which takes the location and scale as the first inputs. We specify size to be the default, none, just like NumPy defaults to none. We give it a name that's optional, and we pass the random number generator. Okay. The graph looks like this. It's just the inputs we had of the normal random variable in a different order. First comes the RNG, then this is the size none. It gets converted to an empty list. This is just a code for the type of the variable. 11 stands for a float 64. This usually you can ignore. And then the parameters of the distribution come afterwards, so the location and the scale. And all random variables in Aesara follow this format. The first three variables are always random number, size, output dtype, and then the parameters of the distribution in order. Okay, so we'll just compile a function, take as input the location, output the normal, and we'll evaluate it with a location of 0. We'll get a random draw. I'll call it again, and I'm going to get the same value because the inputs are exactly the same. That might be a bit surprising, but all Aesara graphs or functions, they are deterministic operations or deterministic functions of the inputs. So if you don't change the inputs, you get the same output. And in the case of random variables, one of the inputs that's very relevant is this random number generator, which tells the state of your random number generator. And if you want a different value, you have to update these. So we can, in this case, just call set value, because this was a shared variable, so it's a constant we can mutate. So we just set it to a new random number generator with a different seed. And now if we call it, we'll get a different value for the function. Okay. Again, it's going to be the same across evaluations. So what happens in Aesara when you are taking random draws is every time you call the function, you are updating the random number generator behind the scenes so that you get different draws in every call. And this is actually exactly what NumPy does. If you are more familiar with how random number generation works in NumPy. Now, this is obviously a bit cumbersome for users, so there are utilities both in Aesara and also in PyMC to make our lives easier. So in PyMC, you can use from the Aesara F module, you can use a handy compile PyMC, which is just a wrapper around the Aesara function. So you pass inputs, outputs, you can pass a random seed, and it will make sure to create a function that every time you call it will update all the random seeds that are present in the function. And now you can call it multiple times and you'll always get different values. Okay, I will take just, if there's one or two questions, I will take them quickly before I go to the next section.
I've mainly been answering questions in chat. So yeah, but like if someone has one, maybe just unmute yourself and then you can ask, but otherwise I think we can continue.
That's also cool.
Which I think you may need to raise your hand and then you can be unmuted.
Okay. So I will continue. Feel free to post in the chat and I will collect the questions in the next break. Or I see that some people have been answering. That's also a good way to get your replies. So now that you have a crash course in Aesara and the random number generator in Aesara, I'll just show you how PyMC makes use of these functionalities to do two of the most important operations in the Bayesian workflow, which are taking prior predictive draws from a model and doing posterior predictive draws from the same model. So the first thing to know about PyMC is that these things we call distributions in PyMC are just functions that return random variables. If you call pm normal.dist, so just so I can create a normal random variable outside of a PyMC context, what you get back is the familiar normal random variable with the exactly same type of inputs. Again, you can compile it and you can call it several times to get random draws. And if you call it inside the model context, it's exactly the same, except we also register some meta information in the model object. So in this case, we don't call the .dist, we just call pm normal. We give it a name, mu, tau, some size. And again, its output is still just going to be a random variable with just different inputs. For instance, a size of 2. Okay. I don't know why I had xeval. I will take it. Well, I'll show you. Okay, so like every Aesara variable you saw, you can call eval on it. In this case, it takes no extra inputs because all the inputs were constant. Of course, if you call it multiple times, it's always going to be the same because no input was changed, including the random number generator. We could compile a function to just take random draws, but because this is so useful and handy, we just have a helper in PyMC called pm.draw. You pass any variables, you specify how many draws you want, and it will take care of compiling the function and calling the given number of times, and also concatenates the outputs, I think. So this is a handy way if you just want to debug models, just put the variables, take draws, see if they have like the right shape or values that seem reasonable. And then a PyMC model is basically this. So when you create a PyMC model, you're just creating an Aesara graph that usually has multiple random variables and some also tensor operators on random variables. So this will be a graph that I will be reusing multiple times during this talk. So let me just present it. We'll define a mu variable that follows a normal distribution, a unit normal, then a log sigma variable that also follows a unit normal. And then we'll have a likelihood. It's a y variable that follows a normal, whose mean is the mu and sigma is the exponent of log sigma. And we say that we observe the values 4, 5, 6. Okay. In plate notation, this looks like this. And if we just output y, we'll see that this looks, if we just deprint y, we'll see it's just a graph, Aesara graph made with 3 random variables. The output is our y variable, who has as inputs for the location mu, which is itself a random variable, a normal random variable. And for the scale, it takes the exponent of the log sigma. Okay. All these variables, because they were created in a model context, are stored. So in the model.free RVs, you get the random variables that are not observed, our mu and log sigma. In model observed RVs, you get the likelihood, y, and the basic RVs contains both free random variables and observed random variables. Okay, so at this step, we are ready to do prior predictive sampling and posterior predictive sampling with PyMC models. Prior predictive sampling is very simple. We just compile again a PyMC function. We compile a function that will take care of doing the update of the random number generators. In prior predictive, usually you don't have any inputs, and the outputs will be all the random variables in your model. The free random variables will be the prior, and the observed will be the prior predictive. But usually we use a single function to take both draws. We compile the function, we can call it twice, and we are getting draws from the prior predictive or getting predictive draws from the model. And this is not very different from what happens when you call pm.Sample predictive, except some more massaging of the output goes on, so that, for instance, if you call it by default, you get a dictionary with the values concatenated for all the variables. And if you call with inference data equals true, you get an inference data object with your prior draws, mu, sigma, and in prior predictive, you have y. But behind the scenes, not much more is happening than creating this function. Right, posterior predictive, it's almost as easy, except this will be a function whose outputs are usually the observed random variables only, and the inputs, we actually will pass values in place of the free random variables, those that we sample during posterior sampling. This is very similar to in the example above when I showed that you could create a function that has as inputs intermediate nodes. So when we had a function of y in terms of z instead of x and y, you can think here that we have a function of the random variable y, not in terms of the random draws of x and wait, what was the name? Mu and log sigma, yeah. But it'll be some values that we input into the function that have the same shape as mu and log sigma would. So we create that function. We'll just create some dummy values. Let's say we took two draws from the posterior, and mu was 5 in the first draw, the first sample, and 12 in the second, and log sigma was -2 and then 1. And posterior predictive is just basically looping through the values and then calling the function with these values as inputs once at a time. And here we have 2 posterior predictive draws for y. And this is very similar to what you would get when you do this, except instead of manually specifying the values, you usually sample them. All right. So I'll make another break if there's new questions before I jump to the next section. Okay. Seems like.
Yeah, there's a lot of discussion in the chat, so you're good.
I'll go. All right, AePPL is a new library in the ecosystem of PyMC and Aesara. AE is the prefix we are using for all the Aesara-like libraries. So this can be read as Aesara Probabilistic Programming Language. And this is a new library that I'm really excited to share with you, who has a very narrow goal, which is convert graphs, Aesara graphs made of random variables, into log probability graphs. We'll go a bit to what this means and also what it can do in part, how to say that. So a cool thing about AePPL is that you can define graphs that are not made just of raw random variables, but you can actually condition on some operations on random variables. I'll show you examples of that. And these include vanilla tensor operations like exponentiation, logarithm, multiplication, indexing, conditionals, loops. It supports variable transformations, which are almost are completely critical for net sampling, for instance. And it also has it does some nice latex output of random variable graphs or log probability graphs once they are converted. So crash course in AePPL will create the most basic random variable graph with just a random normal, a unit random normal. And we'll ask AePPL to give us the log probability of the random variable of this XRV evaluated at 0. Okay. The way we call is AePPL.joint log prob, and we pass a dictionary of random variable to where we want to evaluate the density or the log probability of this random variable. And we get back a verbose graph that just corresponds to basically the density of a normal distribution with some checks to make sure it's mathematically valid. And we can just evaluate. And we get what we'd expect when we evaluate the unit normal distribution at 0, just like we can do here with SciPy. More common, we don't want to just have a function of constant value, but something we can change across multiple evaluations. So we just say, I want to evaluate the density of this variable at an input scalar variable. We just do exactly the same, except now it will be a function of this xvv for value variable, which we can change and evaluate at different points, which would look something like this. Then AePPL can do obviously not just a single random variable, but it can do the graph of multiple random variables. That's why we call it joint log prob. So here is our graph that we already saw in PyMC before with our mu, log sigma, y, but now all built directly with Aesara random variables. And we'll specify that our mu and log sigma will be variables that we pass as input. They'll be scalars, but our y will be a constant. So this is an observed variable. So I always want it to be observed at 3, 4, 5. We call exactly the same function, but the dictionary now includes all the 3 mappings of random variable to point of evaluation. I guess I can print a graph. It's a long graph that has the 3 terms. It just computes a log probability and then adds the terms and then adds the summation of those terms. Okay, so we'll make a function of this joint log prob graph. The inputs will be the mu value variable and the log sigma value variable. The output will be this combined scalar log p. And when we evaluate it, we'll get a number, and we can manually write it ourselves with using SciPy functions just to make sure it's outputting the right results. And that's the main feature of AePPL. And then where the power of the library comes is that you can define graphs that are not just a mapping of a random variable to some input, but this can be an arbitrary expression that built on top of random variables and not a random variable directly only. So the simplest case is this one perhaps. We have a random normal variable, let's call log xrv. We take the exponent of that, and we'll actually ask AePPL to give us the joint log probability of this exponent of a variable evaluated at a given point. For those that are familiar with distributions and probability, this graph corresponds to what's known as a log normal distribution. And if AePPL did the right thing, we should be getting the same output as calling SciPy stats log norm. And that's exactly what happens. The cool thing here is that when we said, when we create a graph that's an exponent of a variable, it didn't need to be a random normal. It could have been any other variable, and you could just have, I don't know, beta takes maybe 2 values. Okay. So we can equally easily create a log beta distribution, not just things that are pre-built, because the rules of how density flows through some deterministic operations are simple to write down. As a more strange case, perhaps in this second example, I will create a vector of 10 unit random variables, and I will take the cumulative sum of them. And I will ask for I can also ask for the probability of this cumulative sum evaluated at a given value. I will not dwell much, but you can just notice that I pass as a value will be just 0 to 9. And the AePPL graph, when evaluated for this value, gives a value, gives for the initial point, and then all the others are just as if you had a normal variable evaluated at 1. Okay, and this is exactly what the probability of a cumulative sum evaluated at these points would be like. So we get the first value just at 0, and then all the others were just a difference of 1. So they are equivalent to evaluating the normal at 1. We'll go one step further and also show you that we can ask the probability of not only tensor operations, but also, or not only these basic functions like exponentiation, log, scaling, but also a bit more funky operations like concatenating 2 vectors of random variables. So I'll create a random variable of size 3, unit 1, and then one with a slightly larger sigma of size 4. I will concatenate them, and then I'll ask AePPL to give me a function that gives the log probability of this stack of 2 random variables. And when I evaluate, what we get is that it figures out that the first 3 values, they should be evaluated at a unit normal, and the last 4 values should be evaluated at a normal with a scale of 2. So this is just, you can think of this, that we created a new distribution that just a concatenation of different pure, let's say, random variables, and we can evaluate the probability of this. And then I'll go a bit, I'll keep digging here. Sorry if I lost you. You folks, you can ask them to revisit this example if it was too fast. So what I'm going to do is just show that you can combine these different kind of operations and nesting, and your AePPL still be able to give you a density for almost an arbitrary graph. So I will create an initial random variable, which is just a log normal again, an exponentiation of a normal. I will create this innovation random variable, so a vector of 9 unit variables. I will concatenate the initial random variable with the innovations. I just padded it, add 1 dimension, and then I will take the cumulative sum. And for those that are familiar with time series, this graph corresponds to a Gaussian random walk, where the initial point follows a different distribution, and then we have innovations that all follow the same distribution. And I can evaluate, and this is very similar to, this is exactly the same you would get if you use PyMC Gaussian random walk with a given init distribution and a given mu and sigma, and evaluate the values 1 to 10, you get the probability back. And if it's not very obvious, the cool thing is that nowhere did we have to tell what is the probability of any of these operations. AePPL was able to figure it out and just give you back the graph when you asked it here. And I think this is the last example. We can do this magic for multiple variables at a time. So I will here create another Gaussian random walk graph where the drift, without an initial point, but we'll have a drift parameter, which is a negative exponential. So we just multiply it by -1, and then we just take a cumulative sum of the 10 normals with that drift and 1 for the scale. And now we have 2 variables, so we'll have a scalar input for the drift random variable and a vector input for the Gaussian random walk. And we'll use a different function that's more core to AePPL, which is factorized joint log prob instead of just joint log prob, which gives you, you pass the same input, a dictionary that says for each random variable or for each variable that you want the density for, what will be the inputs. And it gives you back a dictionary, which has keys are the value variables, these drift VV and Gaussian random VV, and the keys are the graphs that represent the probability of these variables. So I'll just create a function that takes as inputs this drift and Gaussian random walk, and the outputs will be just the values of this dictionary. Okay. And we can just evaluate it. Drift 0 with always the same values for the Gaussian random walk, and we get the log probability of this negative exponential evaluated at 0, which is 0, and the probability of this Gaussian or this cumulative sum with this drift evaluated at 1 to 10. Here I just changed the drift to be -1, so we have now an exponential that allows for negative values. And yeah, this is just I just take the negative of the values 1 to 10. So this is just how show how AePPL can give you a graph of log probabilities conditioned on almost arbitrary operations. And obviously this is what PyMC will use once we start working with log probabilities. Before I go, any new questions? Is there a PyMC example using Gaussian random walk with a unique dist argument? No, but I can show in the end. I mean, I think the doc strings of PM Gaussian random walk should show how to use the init dist. It's just a different distribution as input. And did I read somewhere that PyMC can now automatically exploit conjugacy during sampling where available? We are not yet doing this. We will probably start doing that in the near future. There is another sister library of this ecosystem, AePPL that's working hard on doing exactly that. You give a given model made of random variables and it finds out whether it can sample from the posterior via conjugate sampling or via some specialized Gibbs sampling. So those things are really in the workings, but I'm not going to mention them in this talk. All right, so now we'll see PyMC. How does the probability side of PyMC works? Now that we understand what AePPL can do. And I will just show how it uses AePPL to convert random variable graphs to log probability graphs, and also uses AePPL to create these so-called distribution factories so that users can create more flexible distributions dynamically without we having to create every possible permutation. So yes, PyMC uses AePPL behind the scenes to transform the graph that users define, which, as I mentioned, is a graph made of random variables, into a log probability graph. So here is our old friend model. Just to remind, this is just a Aesara graph of random variables. There's no densities anywhere here. But when you create distributions inside the model, one of the things we do is for every random variable, we create this value variable, very similar to how I was doing it here manually, which is just an input variable of the same type as the random variable. So for the mu, which is a scalar, you'll have a scalar input variable. For log sigma, you'll also have a scalar. And for y, it will be just a constant vector of 3, 4, 5, because y was an observed variable. If you want a log p of a model, you just call model log p, which behind the scenes will just call AePPL, basically passing this dictionary as input. The graph will now be a graph of densities, similar to what we saw before, quite long, but doing what you expect. And we can get the value variables that are not observed from model value vars. And with these, we can create our function to evaluate the model joint log probability. So we just call Aesara function. We pass this input mu and log sigma variables, which are not the random variables, even though they have the same name. I can show that if I just do this, you just see it's a graph that just, when nothing happens, it means there's no operation. This is just an input variable, mu and log sigma. And I think I can also do this, perhaps. Yeah. And you can see they are scalar variables. That's what the parentheses mean, and they are float 64. So this is all these are. So we'll use those as the inputs. The output will be the model log p that we called here with this helper function, which behind the scenes just called AePPL. And now we have a function of the model joint log probability. And because Aesara allows for automatic differentiation, we almost equally easily, we can also get the gradients of our model, in this case by just calling d log p. And I can compile a function of the value variables, the gradient of the value variables with respect to the log p, and evaluate it here 3, 1. I get this. Or I could also pass the model log p. So we have both log p and d log p as outputs. The first output will be the log p, and the second will be the d log p. And one reason why you might want to do this is that, as I mentioned before, Aesara will reuse any shared computations. So if you have any operations that happen in both the log p and the d log p, in this function, they will just be computed once, instead of if you call the function separately for the two outputs. Okay, once you have densities and gradients, you can start doing Bayesian inference. I will not show you, just for the sake of time, how you could just, but you could easily do a Metropolis sampler, or if you know how nuts work, you could write your own nut sampler. You're just using as inputs, or just working with this Aesara function we define. But for the sake of time, I'll show you a more simple form of, let's say, Bayesian inference, which is just finding the maximum a posteriori. So the single point for which the model has the highest posterior probability. PyMC obviously has this under the find map function, which finds that for this model condition on y being 3, 4, 5, the maximum a posteriori values for mu are these and for log sigma are these. If you didn't have PyMC or you had to write your own PyMC optimization functions manually, you could do it, because all you need again is this log p and d log p function. So in this case, you just use SciPy optimization to do basically the same as the find map. We just pass the function, just wrapping in a lambda because SciPy uses a vector and the function expects separate inputs. And we just do negative because we are minimizing instead of maximizing. But once we have that, again, we can just use any routines that are out there to do sampling or to do optimization from a PyMC model. And the last way how PyMC uses AePPL is to build new types of distributions. I will show you an example for how PyMC creates sensor distributions, basically online. I will just generate some random data that corresponds to a censoring process. If you're not familiar with censoring, you can check some of there are very good PyMC examples on censoring, but the data generating process is basically this. We have a parameter that we'll want to recover, which will be the mu true. We'll set it to -1.5. We take random draws from a normal with this mu, a sigma of 1, and we take 10 of those draws. And then we clip the values to be always between -1 and 1. So if you got a -2 point something, that becomes a -1. So the data might look something like this. And you'll see that, yeah, and to then create equivalent model in PyMC, we just create a prior distribution for mu. We create this y raw using the pm normal dist, because we don't actually want to sample or do anything with this raw. It's just an input to pm.Censored, which is it's kind of a factory of distribution. So it creates a sensor distribution of any input distribution. In this case, a normal with this specific mu. Could be a beta, could be anything. We say that we are truncating between -1 and 1, and we pass our observations. And under the hood, this call is just basically returning this graph. at.clip, like we had numpy of y raw -1 and 1, which AePPL knows how to basically derive the probability of this operation, of this clipping operation, which again corresponds in the statistical framework to censoring. So just create a model. I'll not show you the whole graph, but just to prove what I was saying, y is a clipping operation. So it's indeed equivalent to this. We can do predictive. This is how our mu looks before. This is how our y looks before we observed any data. So it's a normal with an excess of -1s and 1s, because all those values get truncated to or clipped to -1 and 1. We can then sample condition on our observed data, which should be pretty fast. And behind the scenes, AePPL gave you the log probability of this graph condition on this specific likelihood. It's something you could take the gradients with respect to. So we are using nuts to sample mu. I think sampling is done, work well. Our posterior is nicely centered around the real mu, which was -1.5. And we can now do posterior predictive draws. And we'll see that after observing data, we expect to have much more -1s and not so many higher values, which is just our model condition on data. And finally, we hope to, in the future, use AePPL to allow users to define their own arbitrary distributions, not just the ones that PyMC offers when you call pm.normal or pm.Censored, but anything that the user knows AePPL can parse or can try to see if it can. And I will just give you an example. This is still work in progress, so there is no nice API for users to define their own distribution. So we'll just do it manually using things that you might not otherwise see. And so in this example, I will write a mixture model in PyMC using AePPL to infer what is the probability of a mixture. So we just start by creating an index variable, which will be a categorical with this specific probability of getting 0, 1, or 2. And this will be of size 10. And then we'll create components. We'll just stack 3 different distributions, roughly centered at -5, 0, and 5 to be easy to visualize. And then what a mixture corresponds to is basically when you have the components, you index it by an integer. And this will be basically you take a draw from the right basically component. And we can define this model. So this is where we used basically AePPL, or we'll use AePPL because AePPL will understand that when you have a stack of distributions and you index by another discrete variable with finite support, this corresponds to a mixture of the components. So we'll have to manually register the variable because there's no way for users to do it automatically. But so we just say, I want to register this mixture variable. I'll give it this name. I'll give it these deems, and I'll just say, take a draw from, use the prior for setting an initial point. You can ignore this second point. This is work in progress. So when you plot when you do the plate graph, it shows actually mixture is a deterministic because it does know that we can have variables that are arbitrary operations on pure random variables, but it will work well, trust me. So we'll just, yeah, we don't need that either. Let me skip this. So I'll just use it to take draws from the prior. This is what the prior of our mix looks like. So just these 3 components with different mixture weights. And now we'll do some inference. We'll use the first draw from the prior predictive as our observed data. So this is the values we observed. And these were the true indexes that were used in these, or meaning the components from which these values came. And so we'll just use exactly the same model, but now we'll say the data is the first draw from the prior, and now we'll do inference on the indexes. Should be relatively fast. We are using the categorical Gibbs metropolis for our categorical variable. Samples pretty fast. And we can confirm that our posterior for the indexing nicely matches what the true values were. Okay. So this just to showcase that thanks to AePPL, we were able to create a mixture distribution ourselves without PyMC doing anything, by just doing, basically creating the graph that when you take draws corresponds to a mixture process, and trusting that AePPL knows that how to then convert this to a valid log probability. All right, I think that's what I wanted to show. So I'll hope you enjoyed it. I hope you didn't get too lost. Probably I went a bit too fast. So if something was confusing, I can revisit the example, or if you just have other questions, just feel free to ask. Okay, Juan has a good question. Which composition operators does AePPL not support yet? Quite a lot. We support basically multiplication, addition, exponentiation, logarithm, and we support some basic. We support indexing. We support for loops. And we support a couple more things like concatenating and stuff, but this is a work in progress. For instance, I think Larry, who is in this, joined the talk, is working for the Google Summer of Code, is working on expanding the range of operators that AePPL support. And we have nice beginner-friendly issues in the AePPL repo to support more operators. So if this is something that you find interesting and you would like to collaborate and expand AePPL, this would be a great way. The ultimate goal is any arbitrary graph for which there's a valid, there's a valid probability function with respect to it, we would like AePPL to support it. Okay, Cole Talon asks, what is the relation between AePPL and Aesara? I have to write an hypergeometric function for a library I'm working on, and I'm wondering which library would be more appropriate. So before that, AePPL is, I here show them side by side, but AePPL works on top of Aesara, right? So AePPL inputs are Aesara graphs, outputs are Aesara graphs. It depends exactly what you want to do with hypergeometric. If you want to create a random variable, something you can take random draws from, that would be pure Aesara code. If you want to define the log probability, that could be done with help of AePPL, or it might just not need AePPL at all if you just define the function yourself. So one thing that the most basic thing that AePPL does is, let me show you the first example. Now I can have the table of contents. Okay, yeah. The most basic thing that AePPL does is just, if you have a certain random variable of a type, you can dispatch a given function that gives the probability of this random variable with the inputs and the value variable. So for your hypergeometric, you might just have a function that when it sees a similar at.random.hypergeometric or whatever object you created, it will know this is the log probability of that distribution. We have in PyMC, yeah, there are two notebooks you can use to go more in depth on these to understand exactly the code where the things are written, of how you can create new random variables and define log probabilities for them in the PyMC docs. Okay. How difficult would it be to support, so Robert Mitchell asks, how difficult would it be to support other data types like polars as an example? Could it be a beginner PR? So the way I read that, the data is still numeric, it's just whether it's interpreted as a polar data. Yeah, so the way we do that in PyMC and AePPL is that we use transformations. So we have, for instance, for the von Mises distribution, we just transformed whatever input to be on the unit circle. I don't know if it would be a beginner PR, but would be good to see if you can implement a distribution that uses polar input values. And if you cannot, then open an issue and ask on Discord to see where the limitations are so that we can unblock that. The hypergeometric is a component of a log likelihood function. Sure, perhaps called open a topic on our PyMC discourse, maybe just exposing what you had in mind, and then I'll be able to give you a more proper answer to your question about the hypergeometric. And in general, any questions about the libraries and what you can do with them, the right place will be Discourse, where we can async give you all the answers. If I missed your question above, just feel free to rewrite it or copy paste it. Otherwise, you can also just raise your hand or join in the chat with voice. Again, the notebook is here.
Wow, awesome. Thank you so much, Ricardo, for an amazing presentation. I definitely learned a lot about how things fit together. And most of all, thanks everyone for joining, for being a part of this community and being interested in how it actually works. So yeah, with that, thanks and have a great day. Stay involved in the various links that we posted and hope you'll join us for the next one.